We're going to start chapter 29 and 30. This will wrap up the school year. So chapter 29 is about solid state electronics. And we're going to talk about conduction in solids today. This kind of is the basis for your microchips. So today we'll talk about conductive and valence bands, how temperature affects conductivity. We'll look at what makes an insulator and a conductor and a semiconductor, and how these semiconductors can be made, since some of them are intrinsic and some of them are extrinsic. So first of all, your electronic devices are made of conductors and insulators. This allows the electricity to flow or not flow. The first electronic devices were made using vacuum tubes that directed beams of electrons, which, remember, moving electrons are electricity. So these vacuum tubes were conducting electricity by shooting beams of electrons. They were super, super big. They gave off a lot of heat, and they had to be replaced every 5 years. So computers back in the, before the 1940s were building size because they had to hold these vacuum tubes. So in the 1940s, after that, they replaced vacuum tubes with solid-state conductors, which are made out of silicon and uranium. These are pretty much what your cell phones are made out of, your computers, your clickers that are sitting in front of you. Now, silicon and germanium, are semiconductors, and they will work with very weak electrical signals, so they don't give off as much heat. So they don't take as much power to run. They don't take a bunch of space, and they don't have to be replaced every 5 years. Okay. So let's talk about the band theory of solids. The band theory has to do with where the electron is based on its energy level. So if something with a low amount of energy is going to be more in the ground state, and it's not going to have enough energy to get away from the atom. So let's look at carbon. Carbon is an insulator. Between its two states, right, the ground state and the next electron, well, wherever it can get far enough away. Let's say it's just an excited state. I don't know what energy level it is. But the ground state is its valence band. This is where it does not want to get away from its atom. The atom pulls on it too much, the nucleus pulls on it too much for the electron to get away. This is what makes it an insulator. But if we're able to excite that atom, if we give it 5.5 electron volts, the electron will get in a high enough energy state that it will be able to escape the atom. Now remember, we can't give anything in between because let's say that this is the ground state and this is energy state 2. Right? It can't hit anywhere in between. So that's why it's called the forbidden gas. Now if you look at silicon, silicon is a little bit different. It still has a valence band. This is where it's nice and close to the electron, or to the atom, the nucleus. And then a conduction band is where it would actually be a conductor. It's not that far. It's about 1.1 electron volts. So most semiconductors of silicon have a gap of around or lower than 1 electron volt. This means it doesn't need that much energy to become a conductor. So it can become a conductor if you just put a little bit of electricity into it, and then boom, the electrons start to flow across the surface because you can excite those electrons to the next state very easily. Whereas here, this is going to take a lot of energy, so it doesn't conduct easily. So it's not considered a semiconductor. Now, a conductor is going to happen where these things overlap. So any of the elements, which are metal elements, are going to be right in here. Those elements are all conductors because these things are going to overlap. But carbon, way out here, has a huge energy gap. There's lots of stuff in between. And then silicon, you get your energy gap. So conduction band, valence band. So the theory pretty much states that when the electron gets enough energy, it will cross that forbidden gap into the conduction band and it becomes a conductor. Now, these bands are going to depend based on your element, and that means the electron's distance from the nucleus. And any element that has bands that overlap are good conductors. Those are your metals, like copper.
It's by my mind. I don't know why I was thinking. I read it and I was like, oh, Diana.
Okay, so conductors. With conductors, all you have to do is put an electric potential across the surface. So on one side, you have a high density of charge, and here you have a low density of charge, and the charges are going to move across the surface. Now, remember that electrons in a conductor, they don't move in straight lines because they have wave nature, and they're kind of random, and they're all over the place. But overall, they're going to move from the high density of charge to the low density of charge to spread out. This is called drift speed. Now, we did talk about this a little bit earlier. So things that are good conductors have partially filled electron bands. Their valence band and conduction band overlap on that chart. And the electrons, since they're partially filled bands, or partially filled outer shells, it doesn't really matter if they lose or gain an electron. Overall, it's not really going to affect the atom that much. Where your insulators tend to be on the outside of your periodic table, and where they really want to hold on to those electrons because they have a filled shell. And so they don't tend to be conductors unless you give them a lot of energy and excites those electrons to a higher state. Then it will be a conductor, but it takes a lot of energy, so we don't call them conductors. But these conductors, these metal ones, they overlap, so they don't need any energy to share electrons. They're going to do it anyways. Those are called conductors. Okay, here's a picture of that electron drift speed. Again, atoms or electrons are moving around fairly randomly, but for the most part in one direction. That's what creates your electric field, which creates your electricity. The higher the temperature of the wire, the more the atoms vibrate around, and with more movement comes more chaos. So the electrons are going to get bumped around more, which means they're going to slow down. So a higher temperature means it's going to be more resistant. Okay, so insulators. Here's a picture on the top of an insulator. It's conduction band. It takes about 5 electron volts to get from the valence band to the conduction band. That is a large amount of energy, so it's an insulator. Semiconductors here only require around or less than 1 electron volt. So that would be considered a semiconductor, meaning it doesn't need that much energy to conduct electricity. Okay. Here's your semiconductors. The band is around 1 electron volt. It should be less than 1 electron volt. So anything from 0 to 1 electron volts is the forbidden gap. Silicon and germanium are the most widely used semiconductors in their in the microchip world, and that's because they have 4 valence electrons, which is exactly half a shell. So as they heat up, they're going to become less conductive, and that's why when your electronics overheat, they die, because the information can't get from one side to another. I had a laptop when I was in college and only lived about 2 years because it kept heating up. And when it heated up, it would freeze. The computer would freeze, right? And that's because the electrons, they can no longer move from one place to another because it's not conductive anymore. So that's why your phone, if it gets super hot, a lot of times it won't work, because the electrons, the information, can't get where it needs to go. Now, there was this neat NOVA presentation that I was watching by Neil deGrasse Tyson, one of his older science ones. I can't remember what it's called, but they were talking about diamonds as being the next semiconductor, but only diamonds that were made in a lab, because the diamonds made in a lab are pure diamonds. They don't have anything else in it. Natural diamonds always have some sort of flaw. They have, you get some of your pink diamonds, some of your yellower diamonds. Every natural diamond has some sort of flaw in it, so they can't use those as conductors. Hello? Sure. Brandon, front office. So the next thing they're thinking about using is these lab-grown diamonds as semiconductors. You guys ever seen those history channel type things on the crystal skulls? No? Nobody? There's like 9 crystal skulls that they found all over the world. No? Okay. Anyways, they think that because of this like diamond, like they're made out of solid quartz. They don't know how they made them. They think that they actually store energy or they do something because it's a crystal structure, right? So it either stores energy or it can conduct to some sort of information. So it's kind of, that's what I always think of when I'm thinking about this stuff. Those crystal skulls, man, they got to be important somehow. I still don't know how they're made. There's no marks on them. All right. All right, with some semiconductors, since the valence electron has shifted to the conduction band, right, so you add a little bit of electricity to this electron, it excites it up, and now there's a hole that needs to be filled. This hole is going to conduct the next electron. So that electron falls in it, and then it gets excited, and then there's another hole. So these electrons are falling in the hole, getting excited and moving up, and then they'll fall into the next hole. So that is how semiconductors work. They're like these little bunny hops of the electrons as they move along. For some semiconductors, the intrinsic ones, they only need heat. If you just add a little bit of your heat to it, it'll start to conduct electricity. And that's because just that little tiny bit of energy that it's taking from your hand will give it enough energy to excite the electrons, which will allow the electrons to start flowing. They leave a hole and then they move on. That's an intrinsic semiconductor, something that does it naturally. Okay, here's a picture of an intrinsic semiconductor, or a diagram. The electron, it gets excited, it leaves a hole behind, and the next electron will fall into it. So extrinsic semiconductors are semiconductors that we make to do this. They don't really do it naturally, or not as easily naturally. So we actually have to put dopants in them, meaning other materials. So one of the things that we do to silicon is put an arsenic donor into it. So the arsenic atom sits in the middle of silicon, and it's a donor, so it has an extra electron. Another type of element that we'll add to silicon is gallium. Gallium, it'll have a missing electron, so it's an acceptor. So you put the donor next to the acceptor, and the electron will naturally move to this one. And then it gets excited, and then to the next one. So these are extrinsic semiconductors, something that we make to do this, where intrinsic is naturally done. Now these two types of semiconductors, the first one is N, the negative type. Right? Negative meaning it has an extra electron. So the donor is going to be an N type, extra electron. And then the other one, P type, is positive, so it's missing an electron. So overall it's positive, it has a hole. I've got one more slide of information when you guys are ready. Okay, here we go. And that that is thermistors and light meters. And by thermistor, I mean like a thermoresistor type thing. So not like a thermistor like you would use to drink out of. So thermistor is a type of semiconductor that becomes more conductive as it gets heated up, which is weird, right? Usually, the hotter an object gets, the more it vibrates, and the more resistive it becomes. But instead, with thermistors, it's going to become a semiconductor, or it's a type of semiconductor, that the heat of just your hand excites those electrons to the next bond and allows them to the next level and allows them to move right across the surface. And the last little bit is a light meter, and that is saying that it becomes a conductor when light hits it. Now sometimes it has to be certain types of light, but the electrons will take their energy from that light. Remember, it has to be the perfect wavelength of light for it to excite it to the next level. And when it does that, now it's on top, and the electrons will flow right across the surface. So the first one, conductive with heat. The second one, conductive with light. And then I have 6 clicker questions for you. Okay, here's our first clicker question. What happens to conductors as the temperature rises? All right, we have some answers here. As the temperature rises, most conductors, unless it's a special one, the resistance will be increased, so the conductivity will be reduced, meaning that C is your correct answer. Okay, question 2. The energy gap between the valence band and the conduction band for a semiconductor is... Okay, that's some answers. For a semiconductor, it needs to be 1 electron volt or less. I think silicon is like 1.1. Question 3. Why are dopants added to intrinsic semiconductors? Okay, we have some answers. Dopants are added to intrinsic semiconductor materials to increase their conductivity. Question 4. A p-type semiconductor conducts electricity with Still waiting on a few people. Okay. A p-type semiconductor is positive, so it must be missing an electron, which means it's going to conduct electricity with holes. All right. Hopefully we're listening to that one. This question, question 5. An n-type semiconductor conducts electricity with Okay, missing just a couple people. Okay, here we go. If it's an n-type semiconductor, it means it's negative, so it must have an extra electron. All right, last question. This is a calculation question. I'm going to help you answer because there's going to be one like this on your homework. This is cadmium. Cadmium. Not like Cadbury bunnies, although it would be pretty cool. Okay, cadmium has 2 free electrons per atom. So we have 2 electrons per atom. How many free electrons? So we're looking for electrons. How many free electrons per centimeter cubed of cadmium? And I give you some constants. Now these constants you can find in the back of your book. You can look at Appendix D. It'll be on page 913 and 916. So the density I looked up in 913, the density of cadmium is 8.650 grams per centimeter cubed. And then I found its molar mass, which is on the periodic table, which is in 916. So look for cadmium on the periodic table. Look at its molar mass down there at the bottom. And I believe molar mass is capital M. Be 112.411 grams per mole. So how do we get from electrons per atom to electrons per centimeter cubed? We can ignore the electron part. We just need to get to atoms per centimeter cubed. We need to create a trail. Let's start with this. 2 electrons per atom. Now we can go from grams. So we need to get to centimeters cubed. We can go from grams to moles. So we need to get from atom to mole. How do we do that? Atom to mole. So atom's on the bottom here. We're going to put atom on the top here. We'll put mole on the bottom. How many atoms are in a mole? 6.02 times 10 to the 23rd in 1 mole. Okay, now we get to go to moles to what? Moles to grams, because that's what we have here. So moles is on the bottom, put moles on the top, grams on the bottom. This is 112.411 grams per mole. So I put it on the bottom next to the grams. And now We need to get from grams to centimeters cubed, so we're going to use this one. Grams is on the bottom, grams will go to the top, and centimeter cubed is going to go down here. So that is 8.65 per 1 centimeter cubed. And that should give us, cross your atoms out, cross your moles out, cross your grams out, electrons per centimeter cubed, which is what we're looking for. So put that into your calculator. You're going to get some number times 10 to the 22. So I already told you that. And you're going to put that number in the clicker. And when you're finished, you put your clicker away. No killing people. It's not good.
I'm going to severely harm them. 5 minutes. You need 5 minutes.
Okay, I'm going to end it. If you don't have a number in yet, you should put one. Okay, here we go. When I did it, I got 9.26, I think, times 10 to the 22nd. That's what you got? Good. Looks like 10 people got it. Very nice. 9.26? Yep. Okay, and your homework is going to be 1 through 11 and 16 through 20 in chapter 29. And here are your high scores for today. Looks like we have 3 high scores. Good job.